Hi friends, in this chapter we derive a result involving the maximum value of the moduli of analytic functions. For that we begin with a lemma. The lemma says that suppose that mod f set is less than or equal to f of z naught, modulus of f of z naught. At each point z in some neighborhood mod z minus z naught less than epsilon, in which f is analytic. Then f of z has the constant value f of z naught throughout the neighborhood. Proof: suppose f is analytic and mod f of z less than or equal to mod f of z naught, at each point z in some neighborhood mod z minus z naught less than epsilon. Let z1 be any point other than z naught in the given neighborhood. Let mod z minus z naught is equal to rho, and let C rho denotes the positively oriented circle mod z minus z naught is equal to rho centered at z naught and passing through z1. Then by Cauchy integral formula we get f of z naught is equal to which is equal to 1 by 2 pi I, using in Cauchy's integral formula it is 1 by 2 pi I integral over C rho f of z by z minus z naught dz. The parametric representation of C rho is z is equal to z naught plus rho e raised to I theta. Of course, this theta lies in between 0 and 2 pi. That is 0 less than or equal to theta less than or equal to 2 pi. Then f of z naught. Then f of z naught is equal to 1 by 2 pi I integral over C f z by z minus z naught dz, which is equal to this we can write, which is equal to 1 by 2 pi I integral over C, and again the C is in between, that is it ranges over 0 to 2 pi. So, no need of writing integral over C. So, it is in between 0 and 2 pi. So, integral 0 to 2 pi f of z naught plus rho e raised to I theta by rho e raised to I theta into I into rho e raised to I theta d theta, which is equal to 1 by 2 pi I and I get cancelled. So, it is 1 by 2 pi integral 0 to 2 pi. So, what remains? It is f of, we can cancel rho e raised to I theta and rho e raised to I theta. So, it becomes f of z naught plus rho e raised to I theta d theta. Mark it as equation number 1. Hence, modulus of f of z naught, it is modulus of f of z naught, it is less than or equal to 1 by 2 pi integral 0 to 2 pi modulus of what? F of z naught plus rho e raised to I theta d theta. Equation number 2. Since modulus of f of z is less than or equal to modulus of f of 0 at each point is set in mod z minus z naught less than epsilon, we can say modulus of f of, here we have modulus of f of z naught plus rho e raised to I theta is again less than or equal to modulus of f of z naught. Of course, the theta is in between 0 and 2 pi. That is modulus of f of z naught plus rho e raised to I theta. It is less than or equal to f of modulus of f of z naught. Equation number 3. Hence, integral 0 to 2 pi modulus of f of z naught plus rho e raised to I theta d theta is less than or equal to integral 0 to 2 pi mod f of z naught d theta, which is equal to 2 pi modulus of f of z of 0. Therefore, modulus of f of z of 0 that is modulus of f of z naught greater than or is equal to 1 by 2 pi integral 0 to 2 pi f what we have f of z naught plus rho e raised to I theta d theta. That is modulus of f of z naught greater than or equal to 1 by 2 pi integral 0 to 2 pi. Yeah, here we have modulus of f of z naught plus rho e raised to I theta d theta. Equation number 4. From inequality 2 and 4 we get what? Mod f of z naught is equal to, in the equation 3 it is less than or equal to, here it is greater than or equal to. So, modulus of f of z naught is equal to 1 by 2 pi integral 0 to 2 pi modulus of f of z naught plus rho e raised to I theta d theta. Then integral 0 to 2 pi modulus of f of z naught minus modulus of f of z naught plus rho e raised to I theta d theta is equal to integral 0 to 2 pi mod e f of z naught d theta minus integral 0 to 2 pi modulus of f of z naught plus rho e raised to I theta d theta. That is, we are splitting that mode. It is equal to, that is our LHS is integral 0 to 2 pi modulus of f of z naught minus f of z naught plus rho e raised to I theta d theta. This equal to integral 0 to 2 pi modulus of f of z naught d theta minus integral 0 to 2 pi modulus of f of z naught plus rho e raised to I theta d theta. So, this is equal to 2 pi modulus of f of z naught minus integral 0 to 2 pi modulus of f of z naught plus rho e raised to I theta d theta, and this is equal to 0. That is, integral 0 to 2 pi modulus of f of z naught minus modulus of f of z naught plus rho e raised to I theta d theta is equal to 0. The integrand in this last integral is continuous in the variable theta, and from inequality 3 it follows that the integrand is greater than or equal to 0 on the entire interval 0 less than or equal to theta less than or equal to 2 pi. Then, since the value of the integral is 0, the integrand must be identically equal to 0. That is, modulus of f of z of 0 minus f of z naught plus rho e raised to I theta is equal to 0. Hence, modulus of f of z naught plus rho e raised to I theta is equal to modulus of f of z 0. That is, modulus of f of z plus rho e raised to I theta, which is equal to z naught. F of z naught plus rho e raised to I theta is equal to modulus of f of z naught, where 0 less than or equal to theta less than or equal to 2 pi. This shows that mod f of set is equal to mod f of z naught for all points z on the circle mod z minus z naught is equal to rho. Finally, since z1 is any point in the deleted neighborhood, 0 less than mod z minus z naught less than epsilon, we see that the equation, that is mod f of z is equal to mod f of z naught, is in fact satisfied by all points z lying on any circle mod z minus z naught is equal to rho, where 0 less than rho, this rho is less than epsilon. Consequently, mod f of z is equal to mod f of z naught everywhere in the neighborhood z1 mod z1 minus z naught less than epsilon. We know that when the modulus of an analytic function is constant in a domain, the function itself is constant. Thus, f of z is equal to f of z naught for each point z in the given neighborhood. Next, we have theorem maximum modulus principle. If a function f is analytic and not constant in a given domain D, then mod f z has no maximum value in that domain D. That is, there is no point z naught in the domain such that modulus of f of z is less than or equal to modulus of f of z naught for all points z in it. Proof: given that the function f is analytic and not constant in a given domain D, we have to prove that mod f z, that is this mod f z, has no maximum value in that domain D. For if possible, let there exist a point z naught in D such that mod f z is less than or equal to mod f of z naught for all z in it. Let W be any point other than z naught in D. Draw a polygonal line L lying in D and extending from z naught to W. Let D be the short distance from points on L to the boundary of D. When D is the entire plane, D may have any positive value. Now choose a finite number of points, that is z0, z1, z2, etc. zn, finite number of points. So, up to zn along L such that zn is equal to W and modulus of zk minus zk minus 1 is less than D for all k is equal to 1, 2, 3, etc. up to R. Now, construct a finite sequence of neighborhoods, that is n0, n1, n2, etc., n minus 1, nn, where this nk has center zk and a radius D. Since each neighborhood is contained in D, f is analytic in each of these neighborhoods. Also, from that construction, it follows that center of each neighborhood nk lies in the neighborhood nk minus 1. Since modulus of fz was assumed to have a maximum value in D at z0, it also has a maximum value in n0 at that point. Hence, according to the preceding lemma, we have fz has the constant value f of z0 throughout n0. In particular, f of z1 is equal to f of z0. This means that modulus of f of z that is modulus of f of z is less than or equal to modulus of f of z1, which is equal to modulus of f of z0 for each point z in n1. Applying the preceding lemma again, fz has the constant value f of z1 throughout n1. Hence, f of z is equal to f of z1 is equal to f of z0 for all z in n1. Since z2 is in n1, we have f of z2 is equal to f of z0, and hence modulus of f of z less than or equal to modulus of f of z2, which is equal to modulus of f of z0. That is, it is less than or equal to modulus of f of z2, which is equal to modulus of f of z0 for each point z in n2. Therefore, the lemma is once again applicable, showing that f of z is equal to f of z2 is equal to f of z0 for all z in n2. Now, continuing in this manner, we eventually reach the neighborhood nn and arrive at the fact that f of w is equal to f of w is equal to what? F of zn, which is equal to f of z0. Since w is an arbitrary point other than z0 of D, we may conclude that f of z is equal to f of z0 for every point z in D. This is in contradiction with the hypothesis that f is non-constant in the given domain D. That is why, because hence our assumption is wrong, and so modulus of f of z has no maximum value in D. So, next a corollary. Suppose that a function f is continuous on a closed bounded region R and that it is analytic and not constant in the interior of R, then the maximum value of mod fz in R, which is always reached, occurs somewhere on the boundary of R and never in the interior. Proof is like this. For a given f is continuous, here it is given f is continuous and analytic on a closed bounded region R, then the modulus, that is mod f of z, is a real valued continuous function on the closed bounded region R. Hence, this mod fz has a maximum value somewhere in R. That is, there exists a non-negative constant m such that mod fz is less than or equal to m for all points z in R, and equality holds for at least one such point. If fz is a constant function, then mod fz less than or equal to m for all z in R. If, however, is not constant, then according to the theorem, that is our maximum modulus principle, mod fz not equal to m for any point z in the interior of R. Hence, mod fz is equal to m somewhere on the boundary of R. Remark. Suppose that a function f is continuous on a closed bounded region R and that it is analytic and not constant in the interior of R, assuming that fz not equal to 0 anywhere in R and applying the corresponding result for maximum values to the function gz is equal to 1 by fz, we can prove that mod fz has a minimum value m in R which occurs on the boundary of R and never in the interior. Second remark, when the function f in the corollary is written, that is fz is equal to uxy plus ivxy in the component function uxy, also has a maximum value or a minimum value in R which is assumed on the boundary of R and never in the interior where it is harmonic. This is because the composite function, that is gz is equal to exponential of f of z, is continuous in R and analytic and not constant in the interior. Hence, it modulus, that is modulus of g of z, that is our g of z is exponential of f of z, and we can write mod g of z is equal to it is equal to exponent u x y. Which is continuous in R, must assume its maximum value or otherwise minimum value in R on the boundary. In view of the increasing nature of the exponential function, it follows that the maximum value or the minimum value of u x y also occurs on the boundary. So, we can do some examples. Consider the function f z is equal to sin z. And the closed bounded region are such that 0 less than or equal to x less than or equal to pi, 0 less than or equal to y less than or equal to 1. Find the points in R where mod f z has its maximum and minimum values. Solution. The function f z is equal to sin z is continuous on the closed bounded region R where 0 less than or equal to x less than or equal to pi and 0 less than or equal to y less than or equal to 1. And also it is analytic and not constant in the interior of R. Then the corollary to the maximum modulus principle tells us that the modulus of the entire function, that is f z is equal to sin z, has a maximum and a minimum value in R that occurs somewhere on the boundary, not in the interior of R. Now, mod f z is equal to mod sin z, which is equal to square root of sin square x plus sin h square y. From the above equation, it follows that mod f z is maximum when both the sin square x and sin h square y are maximum, and is minimum when both sin square x and sin h square y are minimum. The term sin square x is greatest when x is equal to pi by 2 and is least when x is equal to 0 or x is equal to pi. Since sin h square y is an increasing function, sin h square y is greatest when y is equal to 1 and is least when y is equal to 0. Hence, the maximum value of mod z in R occurs at the boundary point pi by 2 1, and the minimum value of mod f z is in R occurs at the boundary point 0 0 and pi 0. So, thank you for watching this session. See you next time. Till then, take care.